那今天我们要来介绍一个叫做 homogeneous linear system 的东西。其实我们已经看过它很多次了。Today we are going to introduce what is a homogeneous linear system. So a system of linear equations is said to be homogeneous systems if it can be written in the form ax equals 0. And such a system, ax equals to 0, always has at least one solution, which is x equals to 0. The zero vector always solves ax equals to 0. And such a solution is usually called the trivial solution. So this thing has been introduced back and forth in many times. And for a given equation ax equals 0, this homogeneous system, the important question we ask is whether there exists other solution than x equals 0, which is non-trivial solution. So if there's a non-trivial solution, it means that there exists not unique solution for such a homogeneous linear system. So we are talking about the same thing, but by introducing a different concept, which is homogeneous system, you see the exactly the same sentence are restated in a different way. And it can also be said in the following way, which is the homogeneous equation ax equals 0 has a non-trivial solution if and only if the question has at least one free variable. Okay, we were going to see the following examples and then return to these statements, and you will see what the meaning of this one. So the first example asks us to determine if the following homogeneous system has a non-trivial solution. Non-trivial solution means that solution other than x equals 0. And then describe the solution set. So basically the question has two parts if you're answering as a quiz. Of course, it's not. So far, it's just an example. But there are two parts. The first part is that we first need to determine, follow the order. 照着指令去做。第一件事情，我们必须要先决定是不是有 x， x 为非零的情况出现。然后第二步，必须要去描述它的 solution set 是怎么样。Solution set. Okay, so we are given such a homogeneous system. Then we can write the augmented matrix by putting A matrix right next to the 0 vector, put them side by side together. And then do the Gaussian elimination. Eventually, we reach a echelon form like this. And now we identify a free variable. Here it says that the free variable is x3. x3 is a free variable. It's like this line, this row is all zeros, and then like 0, 0x1 plus 0x2 plus 0x3 equals 0. And then so we say that x3 is a free variable. Here we can say there's no other restrictions related to x3 in terms of the third row. And since x3 is a free variable, we have, according to the previous sentence, the fact we stated here, if we apply this theorem. Sorry, let me. continue to share the screen. Okay, the screen is shared now. All right, I hope we see the screen for now, and then, all right. So x3 is a free variable, and then since there is a free variable, the homogeneous system has non-trivial solution. It should have solutions other than x equals 0. Not only the trivial solution can be the solution. And the next step, we're going to describe, step 2, we're going to describe the solution set. So we can continue the row reduction to reduce the echelon form, further reduce the echelon form, such that the leading entries are 1. And then all the elements above and below the leading entries are 0. And as a result, we can write the simultaneous equations in this way. And we can collect this one as x equals to x1, x2, x3. And then x1 equals to 4/3 x3. And x2 equals to 0, and then x3 equals to x3. So that's how the solution is obtained. Okay, I'll write the same. Of the vector, and then the remaining coefficients are kept inside this vector. 把剩下的数值留在向量之中。And then it becomes the format x3 times v, where v is this vector. And here x3 is factored out of the expression, 就是把 x3 提到vector 的外面。This shows that every solution of ax equals to 0, in this case is a scalar multiple of this vector v. 那所有的 v 这个 vector 乘上任意的 scalar 都会是满足这个 simultaneous equations 的 solution。所以我们要描述 solution set 的方式，就是用这样子的一句话，就是我们必须要把它写得很清楚，就是是一个scalar multiple of d 是我们的 answer， 它的 solution set 我们被要求要 describe 它。Geometrically, the solution set is a line passing through origin 0 in the R3 space. You can also describe that it's the span of V, and then it passed through 0 and passed through V, which is 4/3, 0 and 1. Okay, so this is how we use the fact to answer in questions. Do you have any questions for this example? 好，没有问题的话，我们再往下看下一个 example 哦。那这个操作有一点小复杂，不过呢，因为我们有好几个 example， 所以看完 example 之后可能会比较理解一点。Okay, in example 2, we have a single linear equation. Can be treated as a very simple system of equations. We do not have simultaneous equations. Instead, we only have one equations. And then the example asks us to describe an order. We need to answer. Describe all solutions of the homogeneous system. So, okay, the solution says that there is no need for a matrix notation, and we can solve for the basic variable x1 in terms of the free variables. So whether variables is basic and free, it's the user determined， 就是你可以决定哪一个 variable 作为 basic， 哪个 variable 作为 free。那为什么呢？因为以这里来说，例如说我们选择，我们把x1 视为 basic variable， 然后呢用 x2 跟 x3 来描述它。那这个时候 x1 就会等于 0.3 x2 加上 0.2 x3。但实际上，同学也有办法看出来说，如果我们现在选 x2 作为 basic variable，then x2 也可以被写成，就是多少倍的 x1 加上多少倍的 x3， 也是可以这么做。那但是这个选择的 basic variable 它不一定是 x1， 但是数量是一定的，就是有多少个 basic variable 跟有多少个 free variables 的数量是一定的。因为假如我们选了 x2 作为那一个 basic variable， 那剩下的两个 variable 它一样变成 free variables， 所以我们注定是有两个 free variables。OK， 所以这边说we can choose basic variable to be x1, and then that will let x2 and x3 become free variables. Then we can describe the selected basic variable x1 using free variables. So this expression x1 equals to 0.3 times x2 plus 0.2 times x3 is equivalent to say that we have selected x1 as the basic variable, whereas x2 and x3 are two free variables, like this. Okay, then we can write the general solution using a similar procedure in the previous example. X equals to x1, x2, and x3, and then x2 equals to x2, x3 equals to x3. x1 equals to this expression that we just showed. And then we can separate the effect of x2 and x3. And that would give us this expression. I have the general solution. General means like the 一般，就是它具有一般性，具有一般性的 solution， 就是说，任何所有满足这个 linear system 的 solution， 我们都称它为一般的 solution， 它不是唯一的一个 solution。那相对于 general 的英文词汇，大家知道是什么词汇吗？就是如果我不用 general solution， 它具有一般性；如果它不是一个具有一般性的 solution， 相对于general 这个字，一般，相对于它是 special。special solution 就我们可以找到某一个 solution， 例如说我们要满足这个式子一好了，这个一这个式子，那我们可以选择，例如说 x1 为0，然后我们可以选择3个都为0，那它是一个 special solution， 而且是 trivial solution。我们还可以选择x1 等于1，然后 x2 等于2， x3 等于2，那它也是一个 special solution。但这些 special solution 它们都不足以表达这个满足这个 equation 1的所有 solution， 因为我们被要求要 describe 这个 homogeneous system 的所有 solutions。那因此我们就必须要试图找到一个具有一般性的一个表达式。那刚刚我们在这个 example 以及上面一个 example 所做的步骤都有点像是这个样子，所以我们需要找到general solution set。OK， 那 general solution set 它的表达的方法，就是用我们刚刚的这个方式，先选择其中一个为 basic variable， 然后呢用 free variable 去表示它。那 free variable 就会等于 free variable，x2 就等于x2，x3 就等于x3。这两个是 free variable。这个是 basic variable。然后呢，之后写成两个 vector 相加之后，我们可以再进一步的把 x2 跟 x3 提到numerical vector 的外面。OK， 那 然后在最后再做一些描述。我们的描述有点像是下面的叙述法，比如说我们说 this calculations shows that every solution, all solutions of the single linear equation is a linear combination of the vectors u and v。就是这个x2 乘上 x2 乘上0.310，然后加上 x3 乘上0.201，这个 linear combination 它就是所谓的 general solution， is the general solution。general solution of equation 1， 大概像这样。And geometrically, we can also describe it. We can plot u and v in the graph, and then the span of u and v becomes, span is exactly the meaning of linear combination. Span of u and v is the general solution set, and it's a plane through the origin. 它是一个通过原点的平面，所以这边来说，它应该不是只有这个平面，它是所有通过原点的，通过原点，然后并且通过 UV 的平面。OK， 那这个 example 大家有没有什么问题？ Is there any questions related to this example? Alright, so we can continue to see another terminology. 另外一个专有名词 is called parametric vector form. So the original equation for the plane in example 2, the example we just see, is called a implicit 不明显，潜在的不明显的implicit description of the plane. And then solving the equations amounts to finding an explicit description of the plane as the set spanned by u and v. Eventually, we find out the vector u and v, and then can directly say that the general solution is the span of u and v. This process, and such a expression, the linear combination, is called parametric vector equation of the plane. So I have two expression right now. The first expression is this one. 10 times x1 minus 3 x2. 10 times x1 minus 3 times x2 minus 2 times x3 equals to 0. This one is called the implicit description. And the parametric vector expression is what we have: x2 times u plus x3 times v. This one is called parametric vector equation, or span of uv. Okay. Sometimes this equation is written as x equals to some scalar times u plus some scalar t times v. So that's exactly what we have here. And this is the full length expression of a parametric vector equation. In the earlier example, in example 1, the equation is written as x equals to x3 times v, or x equals to a scalar t times v. It's also a parametric vector equation of a line. So we do not have two terms since we're working on just a line in the first example, example 1. Whenever a solution set is described explicitly with the vectors, as in example 1 and example 2, we say that the solution is in parametric vector form. The general solution is in the parametric vector form. So those are the terminologies. Okay, and let's see one more example. We are being asked to describe all solutions of AX equals to B. So we form the augmented matrix. And then do the forward row reduction, and then obtain the echelon form in this way. So this A matrix is the same as in example 1, but now we are having the right-hand side being different. I have a vector B, 7, -1, -4 given. And thus, now the general solution is written in this way. I have x1 equals to a constant -1 plus 4/3 times x3, and then x2 equals 2. x3 is still free variable. Then the general solution of AX equals to B should have the form. I write x1 equals to -1 plus 4/3 times x3, and then x2 equals to 2. x3 is free variable. When it's free variable, we simply put x3 equals to x3. And then we do the decomposition. We separate the constant part versus the variable part. And then we further factor out x3, move it outside the vectors. And then we call this vector again V, and then call this vector P. And here are some explanation about the P vectors. The general solution eventually is written as a format of x equals P plus T times V. And here the vector P itself is just one particular solution of AX equals to B. Okay, and then we observe that the difference between x equals to TV, what we have in example 1, and this is what we have in example 3. And the difference between them is just this P. Here, P itself is just one solution, one special solution of AX equals to B. And then this relationship holds for all the system of AX equals to B. This is the original linear system. And then in example 1, we work on AX equals to 0, the homogeneous systems of that matrix A. And the difference, the general solution difference between them has this value P being added or not. 那这个范例告诉我们，在处理 AX 等于 B 跟 X 等于0两个系统的时候，那当它们的解都不是唯一的时候，它们的 general solution set 的表达式会是很类似的。那差别只有这个小写的 P 这个 vector。差别只在这个小写的 P vector， 其中 P 呢，它自己是 AX 等于 B 的一个特殊解，某一个解。那因此我们可以用前面的方法来找出T 跟 V， 然后还有这个 P 来表达AX 等于 B 的 solution。那如果在同一题被问到说，那我们是不是有办法知道 AX 等于0 homogeneous system 的 general solution？ 那答案是显而易见的，我们是有办法，就是把这个 P 拿掉，然后剩下的 T 乘以 V 的部分就会是它 homogeneous system 的 solution。Okay, so here's a procedure like how you write a solution set of a consistent system in parametric vector form. The first step would be we can row reduce the augmented matrix to a reduced echelon form. And then we express each basic variable in terms of any free variables appearing in an equations. And then we write a typical solution as a vector whose entries depend on free variable, if any. And then finally decompose X into a linear combination of vectors with numeric entries using the free variable as parameters. Free variables in this example is x3. X3 is the free variable in example 3. And then in example 2, I have two free variable. Basically, x2 and x3 are both free variables. And then in the first example is the same with the third example. And here the free variable is x3. So x3 is written right here as the parameters. And here's we're talking about the link between homogeneous linear system and its original linear system. Actually, we have seen this relationship between homogeneous linear system and original linear system in the example 3. I mentioned that the only difference is that p vectors being added to the linear combination of the general solution set. So this difference is called a translation. Here it says to describe the solution set of AX equals to B geometrically, we can think of vector addition as a translation. The vector addition means vector P, 就是 general solution XV 加上一个 P， 那加上的这个 P 呢被视为 translation， 会被称为 translation. Given V and P in R2 or R3, the effect of adding P to V is to move V in a direction parallel to the line through P and 0. And we call that V is translated by P. V is translated by P to V plus P. So here's P is such a vector, and V is right here. We translate V by P to V plus P. And similarly, if we have each point on a line L, each point is translated by P, then we get a new plane. This is a new parallel line, and it's L plus P. So we are translating L by P to L plus P. So we can say things in this way. And similarly, we can have a parallel solution set of AX equals to B and its homogeneous system. So we say that homogeneous system of AX equals to B is to let the right-hand side B equals to 0. And the solution set has those translation relationship. So we are translating the plane of solution AX equals to 0. So that's exactly AX equals to 0. So collecting all X such that AX equals to 0. And translate by P to the solution set of AX equals to B. So they have this relationship and that addition, meaning that the solution sets are parallel to each other. And next, we are going to revisit the linear independence definitions again. We are given an index set of vectors, and each vectors are in the Rn space. These vectors are said to be linearly independent if the vector equation scalar x1 times v1 plus x2 times v2 plus xp times vp equals to 0 vector has only the trivial solution. This is said to be linearly independent. On the other hand, the set v1 to vp is said to linearly dependent if there exists weight c1 to cp, not all of them being 0, such that the equations c1 times v1 plus c2 times v2 plus plus cp times vp equals to 0 vector. If I have non-zero solutions to solve this equation, then the set of vectors is said to be linearly dependent. So we can see the example. In this example, we are given 3 vectors. And for the first part, we are asked to determine if the set v1, v2, v3 is linearly independent or not. And the B part, if possible, find a linear dependence relation among v1, v2, and v3. So the first thing we should do is to form the augmented matrix and then use the forward row reduction to see whether there has multiple solutions to solve the equations equals to 0, or there's only trivial solution that can solve that equals to 0 equation. So the augmented matrix we form is to put V1 right here, and then V2 right here, and to put V3 right here, and put 0 next to it, and solve this this augmented matrix using row reduction. We get such an echelon form. And we find out that x1, x2 can be claimed as basic variable because we say in the last row, we write x3 equals to x3. And it means that free variable, x3 is a free variable. If you once observe an equation x3 equals to x3, then that variable becomes free variable. But for x1 and x2, they are both basic variables. So each non-zero value of x3 can determine a non-trivial solution of 1. Like we do not need to find this particular solution for x3. Like x3 can be any value because it's free. You can set x3 equals to 3, and then 3 equals to 3, x3 equals to x3. That lines basically restrict nothing from values of x3. 就是 x3 它可以 take 所有的值，然后因为它是 free variable， 那这个情况之下呢，我们就发现说v1, v2, v3 它是 linearly dependent and not linearly independent， 它们不是线性独立的，因为求解这个 augmented matrix homogeneous system 的结果是不只有 trivial solution 可以解决它。那我们还有第2个小题必须要回答。To find a linear dependence relation among v1, v2, and v3, we completely row reduce the row completely row reduce the augmented matrix and write the new system in below. We let the leading entries be 1 and then rewrite it as the simultaneous system. And thus we have x1 equals to 2 times x3, x2 equals to negative x3, and then x3 is still free variable. So we can choose any non-zero value for x3, and then that would give me a corresponding solution of x1 and x2. As long as I fix the value of x3, basic variables x1 and x2 can have corresponding values. So here, say means example, means for example. For example, if I choose x3 equals to 5, then x1 automatically becomes 10, x2 automatically becomes negative 5. And then I can substitute these values into the equations provided in equation 1 provided in example 1. And then we will obtain such a plane equation. And this is one out of infinitely many possible linear dependence relations among V1, V2, and V3. Okay, then next we are focusing on the linear independence of matrix columns, because it has some implications when the independent vectors occur in a matrix and among the matrix column vectors. 接下来我们讨论的是线性独立在矩阵的 column vector 之中它发生的话，它同时还代表了一些现象。假设我们先从一个矩阵出发，suppose we are working with matrix A, and those lower letter A1 to lower letter AN represent the columns of matrix A. And the matrix equations AX equals to 0. We're using the concept of linear combination x1 to xn equals to 0 can be written as x1 scalar times a1 vector plus x2 scalar times a2 vector plus xn scalar times an vector equals to 0 vector. Okay, this one is also a vector. And each linear dependence relation among the columns of A will correspond to a non-trivial solution of AX equals to 0. For now, you should already be very familiar with this statement. And thus, we have the following fact. The columns of matrix A are linearly independent if and only if the equations AX equals to 0 has only the trivial solution. So, example 2, we are asked to determine if the columns of the matrix A are linearly independent. So, we're going to study AX equals to 0 and to see if the trivial solution is the only solution. If the trivial solution is not the only solution of it, that means that the columns of them are not linearly independent. So we work on the augmented matrix by putting A right here and then putting 0 right here. And eventually we obtain such a echelon form. And at this point, it is clear that there are 3 basic variables and no free variables. So the equations ax equals to 0 has only the trivial solution, and thus the columns of A are linearly independent. So here we can separate the size of sets into sets of 1 or 2 vectors, with sets with 3 vectors and above. 接下来我们是把当这个集合里面只有1个或2个向量，还有集合里面有3个以上的向量的定义分开来讨论。我们在 very special 的情况之下，在特殊情况之下，这个 set 它只有1个 vector。A set containing only one vector, say v vector, is inside the set. 那只有自己一个的时候，它有办法说是 linear independent 或是 linear dependent 吗？答案是是的。当只有一个 vector 的时候，我们也可以去讨论它是否是 linearly independent。它是只有一个 vector 的情况之下，我们就说它是，如果这个 vector 本身它不是一个零向量，我们就说它是 linearly independent. So we say that if the set containing only one vector, the vector itself, is it linearly independent or not? It is linearly independent if and only if v vector is not a zero vector. And this is because the vector equation x1 some scalar times the vector equals to 0 well has only the trivial solution when v is not a zero vector. So it satisfies the definitions of a general definition of linear independent set. So even though there's single vector inside the set, it can itself be linearly independent as long as it's not a zero vector. And the zero vector is linearly dependent. If that vector v is 0, then we say that this vector itself is linearly dependent, since any vector, any combinations times any scalar x1 times 0 vector will equals to 0. It has many non-trivial solutions. And next, a set of 2 vectors are linearly dependent if at least one of the vectors is a multiple of the other. 当这个集合里面有2个的时候，要如何判断它是线性独立还是线性相移？那2个的时候也是很容易的，就是其中一个的向量是另外一个向量的倍数。It says it's a multiple of the other. 那一旦观察到这个情况，当两个 vectors 出现倍数关系的时候，我们就知道它是线性相移。Then the set is linearly independent if and only if neither of the vector is a multiple of the other. 那反过来，如果说我们观察到2个 vector 当它们彼此之间没有倍数关系，那我们就直接可以判断它们彼此是 linearly independent. So determining whether a set containing one vector and a set containing 2 vectors are linearly independent or not is very special compared to a general set that containing more than 2 vectors. Okay, so now let's see an example. Determine if the following sets of vectors are linearly independent. In the sub-question A and sub-question B, we both have 2 vectors. So in the first problem, notice that V2 is a multiple of V1, 它是 V1 的倍数关系2倍。And hence, V1 and V2 is linearly dependent. And for sub-question B, the vector, because the set contains only 2 vectors, so we observe that none of the vector is a multiple of one another. So could they be linearly dependent? And then here are some like analysis in between, okay? But the conclusion is that V1, V2 is a linearly independent set. Means that, okay, it's impossible. It's impossible for them to be linearly dependent. They are linearly independent set as long as we find they are not the multiples of one another. Then for a set of two or more vectors， 接下来要讨论两个或以上的 vectors 的定理了。For the first theorem, an index set as of two or more vectors is linearly dependent if and only if at least one of the vectors in S is a linear combination of the others. In fact, if S is linearly dependent and V1 is not zero vector, then some Vj is a linear combination of the preceding vectors. It means that, okay, you can find such a linear combinations for at some index, for some index j, and then using the preceding index from 1 to j minus 1. And okay, so do we have questions for now, like about this theorem? Basically, it says that how do we formally define the linear independence when there are two or more vectors? 当只有两个的时候，它是一个比较特殊的情况，就是我们可以用它是否是用倍数来表达。但是当两个或以上的时候，我们必须要用这一个完整的定义，就是如果它是线性相依的话，代表说它至少会有一个 vectors 可以用其他 vectors 的线性组合来表达。那一旦这件情况没有办法发生的话，那么它就是线性独立。Okay, the next theorem, if a set contains more vectors than there are entries in, if a set contains more vectors than there are entries in each vector, then the set is linearly dependent. That is, any set V1 to Vp is linearly V1 to Vp in Rn space if P is greater than n. So we have a graph like this. So I have 1, 2, 3, 4. N is 3. N is 3. But P is 1, 2, 3, 4, 5. In this case, the columns are linearly dependent. If P is greater than N, then the columns are linearly dependent. Basically, if I can only identify three vectors being linearly independent in the Rn space. Or I can say I can at most identify n vectors being linearly independent in the Rn space. So that's why when you are having 5 vectors in the R3 space, then the columns must be linearly dependent. Then the next theorem, if a set in the Rn space contains the zero vector, then the set is linearly dependent. And we have seen why, because when we are talking about the set containing only zero vector, and that set is linearly dependent. It's linearly independent. So if turns out that the set contains the zero vector, then the entire set becomes linearly dependent. You can find many non-trivial solutions that makes the homogeneous system solvable. Okay, in this example, we are given two vectors, and then we are asked to describe the set spanned by u and v. And then we need to explain why a vector w is in a span uv if and only if uvw is linearly dependent. So first of all, we find out that these two vectors, because we are describing the linear independence of two vectors only, and we find out that they are not multiple of one another. 它们彼此之间没有成倍数关系。So the vectors are linearly independent because neither vector is a multiple of the other. And so they span a plane in the R3 space. And in fact, span UV is the x1, x2 plane with x3 being 0. This is by observation. So we can draw the graph in this way, like U and V, a plane passing through origin and then also passing through U and V. And the entire x1, x2 plane would be the span of it. So now, so far we have answered the first questions. This is done by observation. So you probably won't need any systematic way to solve the example, but then sometimes you need to use your observations. So you need to spend time for a while and to stare at it, watch it, and then eventually conclude that, okay, since I found out that both vector contains zeros in x3 position, so and then I can draw the graph like passing through origin, and then passing through U, passing through V, and then find out that the span of U and V is the x1, x2 plane. And then we're trying to explain the next part, the second part. If W is a linear combination of U and V, then UVW is linearly dependent since one of the vector can be expressed as the linear combination of other vectors. So they are linearly dependent. Conversely, suppose that UVW is linearly dependent. Then some vector in UVW is a linear combination of the preceding vectors. And that vectors must be W since V is not a multiple of U. So W will be in the span of U and V. So it's impossible to have W being outside of the span of U and V. So things like that. The next example, we are now discussing a set containing three vectors. These three vectors are linearly dependent. We are having 2, 1, 4, 2, 1, 4, -1, and -2, 2. And we found out that we can obtain one of the vector by linear combination of the other two, which is okay. If I add 4 subtract 2, it will get me 2, and then -1 plus 2, it will give me 1. So by adding the second one and the third one, and I can obtain the first one. So obviously they are linearly linearly dependent. Plus that, okay, it says that there are 3 vectors, but we are only having a 2-dimensional vector, 3 vectors in a R2 space. Then these 3 vectors must be linearly dependent. So we can directly apply the theorem, this theorem, theorem 8, can be used directly to resolve this example. Okay, it says by theorem 8. Okay, then next, determine by inspection. Again, by inspection means that you do not need to perform any Gaussian elimination or row reduction to see how many solutions they have. But then by observations, we can tell whether they are linearly independent or linearly dependent set. 好，那这题很重要哦。这题是要用目测法来判断这3个 set of vectors 它们彼此之间是否是线性相依。那首先第一个 set， 那判断第一个 set 的原则是，我们现在是一个 R3， 它们的母空间是一个 R3 空间。那但是 R3 空间中却有4个 vectors， 所以4个 vectors 它不可能是 linearly independent， 它们必然是线性相依。所以第一个 A 小题的答案是它们是线性相依的。那如果要找到对应的定理的话，是刚刚的定理8。然后第二小题呢，它的是现在的母空间也是 R3 空间，那有3个 vector。那所以我们要进一步的去看，就是说这3个 vector 里面的数值是怎么样。那我们发现其中有一个 vector 是000，那这时候就要用到定理9，就是只要 vector 0 vector 在这个 set 里面，那么这个 set 必然是线性相依，它是 linearly independent according to theorem 9。然后第3 C 小题，我们在一个 R4 空间中，然后有2个 vector， 那一样它的数量是 vector 的数量没有问题，我们要仔细去看 vector 里面的数值是哪些。那观察，我们盯着它看一阵子之后，发现2个 vector， 然后它们之间有成倍数关系。看起来像有成倍数关系，但实际上没有。OK， 我还想说是题目那个少了一个负号还是怎么样。他说它看起来有成倍数关系，就是第一个 element 除以-3，-2乘以-3得到3，然后呢4乘以-3得到-6，6乘以-3得到-9。但是呢，在第4个 element 的时候呢是失败了，就它们之间没有成倍数关系，虽然很像。那所以呢，他说你没有办法去找到其中一个 vector 是另外一个的倍数，所以它们是线性独立。OK， so I'm going to say it again in English. Basically, this example is quite important because it tests us whether we know how to use the observation to determine the vectors are linearly dependent or not. And for the first question A, there are 4 vectors in R3 space. So 4 vectors in a R3 space, they cannot be linearly independent because the number of vectors exceed the dimension of the host space. And so the answer for question A is linearly dependent. They are linearly dependent. And for question B, we are still in a R3 space, and there are 3 vectors. So the number of vectors is okay. Now we need to look in detail the numbers inside the vectors. And we observe that there is 0 vectors. The second vector is 0 vectors. And according to theorem 9, whenever the set contains 0 vectors, this set must be linearly dependent because there exists more than one non-trivial solutions that can solve the systems of equals to 0 systems. And for question C, we are in a R4 space and there are 2 vectors. So number of vectors is okay. In order to judge whether these 2 vectors are linearly independent or linearly dependent, we need to determine whether one of the vector is a multiple of another. But then we find out that we are very close to a multiple of that because we find out that -2 times -3/2 equals to 3, and 4 times -3/2 equals to -6, and 6 times -3/2 equals -9. We are almost there, but for the fourth entry, for 10 and 15, there does not exist such a relationship of a multiple -3/2 is not working right here. So eventually we find out that they are not the relationship of multiples. And so we determine that they are linearly independent. All right, so this example is important. Okay, so this is it for today's lecture. Do we have any questions for any examples that we have seen today?